Okay, we are looking at probability, and today we're going to start looking at some rules. And the first rule we look at are called the addition rules. And again, keep in mind what probability stands for. It's the likelihood or the chance of an event occurring, and that's locked between 0 and 1. Okay, so as I start utilizing these rules, make sure that your probability makes sense, common sense wise. Okay? All right, for addition rules for probability, we have what's called ME. And what ME stands for is mutually exclusive. Okay, and it's very important if you know what that means. Mutually exclusive. Okay? So, two events are ME. They are mutually exclusive if they cannot occur at the same time. Okay? So, two events are mutually exclusive if they cannot occur at the same time. Another way of thinking about this, they cannot occur at the same time, or they have no outcomes in common. Okay? So another way of looking at that is they have no outcomes in common. Okay? So that's what it means to be mutually exclusive. So before we get any further, I'm going to put some examples down, and let's just talk about if these things are mutually exclusive or not. Okay? All right, so let's do an example. Let's say I select a playing card from a deck of cards. All right? So example 1. For all of these examples, we're selecting a playing card from a deck of cards. Okay? And then I'm going to give you two events, and you just tell me if they are mutually exclusive or not. Getting a 5, comma, getting a 10. All right, I'm selecting one card. The event getting a 5, the event getting a 10. Is that ME or no?
Yes.
Can you get a 5 and a 10 at the same time? No.
Not playing one card.
Right, not with one card. So this is mutually exclusive, right? Cannot happen at the same time. Great. Example number 2. How about getting a ace? And let's do getting a diamond. Are those mutually exclusive?
No.
Why not?
Because you can have an ace or diamond.
Yeah, you can have a diamond that is also an ace. In fact, he's called the ace of diamonds, right? So, no. All right, example 3. Getting a red card, getting a 2. Red, getting a 2. Are those two events mutually exclusive?
No.
No, because you can get a red 2, right? In fact, how many red 2s are there? 2, right? So no. And finally, the last example, a club and a spade. Club and getting a spade.
Yes.
Are they mutually exclusive? Yes. You can't have one card that is both a club and a spade, right? So this is ME. All right, does everybody understand that? Okay, great. If we can understand what mutually exclusive means, then we can do our very first probability rule for addition. And this is what it looks like. So here we go. Addition rule number 1. I'm going to give you 2 addition rules, but you're going to soon see that it's really just one addition rule. And I'll show you in just a few minutes what I mean by that. So here we go. Addition rule number 1. The probability of A or B occurring is equal to the probability that A happens plus the probability that B happens. Okay? This is probability rule number 1, And it's only if A and B are ME, okay? So, if A and B are ME, then this is my rule. Probability of A or B occurring is equal to the probability that A occurs plus the probability that B occurs. This is only true for mutually exclusive events. Okay? All right, let's do a couple of examples. Example number 1. Let's say I select a single card from a deck of cards. Okay? The experiment is I'm going to select a single card from a deck of cards. What's the probability that card is a 5 or a 10? So here's how I would write that. The probability of drawing a 5 or a 10. So before I continue with this problem, are these mutually exclusive? Yes, right? Can't get a 5 and 10 at the same time. So we're just going to follow this rule. It's simply the probability of drawing a 5 plus the probability of drawing a 10. Okay? Now we have to go back and remember classical probability. What is the probability of drawing a 5? Well, how many cards are there? 52. How many of those cards are 5s? 4. Great. Similarly with the 10, right? I have 52 cards. 4 of them are 10s. And this will give me 8 out of 52. And we should be able to reduce that down, divide everything by 4, 2 13ths. Okay? That is a probability of drawing a 5 or a 10. Okay, great. Let's do a club or a spade. So example number 2. I draw a single card from a deck of cards. What is the probability of drawing a club or a spade? These are mutually exclusive events, so I can use addition rule number 1. What's the probability of drawing a club? 13 clubs out of the 52 cards. How many spades are there? Also 13. This gives me 26 out of 52. And that reduces down to 1/2. Great. So you have a 50% chance of drawing a club or a spade. That's it. That is the end of addition rule number 1. And that is the rule that we use for mutually exclusive events. Okay, so a great question that might arise is, what if they are not mutually exclusive? What do we do? If they are not, you use addition rule number 2, which looks like this. Probability of A or B, making this addition rule number 1, turn it to number 2. Probability of A plus the probability of B minus the probability of A and B both occurring at the same time. Okay? Now, just a moment ago, I said I'm going to give you 2 addition rules, but really there's just 1 addition rule. Okay? And here's why. This is your addition rule. If events are mutually exclusive, if A and B cannot happen at the same time, then what is the probability that A and B happen at the same time? 0, right? So you can still use this rule, it's just that this part will be 0 if the events are mutually exclusive. So this rule is really the only rule for both, okay? But it's important that you know mutually exclusive or not. Okay, so let's do the non-mutually exclusive examples that we came up with. What was it, spade or an ace? So let's do, what's the probability of drawing a spade or an ace? So, according to this rule, I do the probability of drawing a spade, then I do plus the probability of drawing an ace, then I subtract the probability of both happening at the same time, getting an ace and a spade together. Okay? So In 52 cards, how many of them are spades? 13. In 52 cards, how many of them are aces? 4. Is everybody with me on that? How many cards do we have both an ace and a spade together at the same time? There's just the one card, right? The ace of spades. Okay? So here's what's happening. I have 13 out of 52 cards, 13 spades. I have 4 aces. But there's one card, the ace of spades, that we've counted twice. We've counted it here with all the spades, and we've counted it here with all the aces. Okay? So that's why we have to subtract off, where we've counted it twice. That's how this rule works. Does that make sense? So if you wrote out your sample space and you circled all of the spades and circled all of the aces, well, if you do it this way, you're counting that one card twice, and that's why we have to subtract it off. Okay? So 17 minus 1 is 16, so 16 out of 52. And we can reduce that down, right? 4 goes into both, so 4 13ths. Okay, great. What about a red card or a 2? Draw a single card from a deck of cards. What's the probability that card is red or 2? Okay. To do this problem, you're going to use the addition rule. What's the probability of drawing a red card? How many red cards in the 52? 26, right? Half of them are red. How many 2s are in the 52 cards?
4.
There's 4. Okay. How many instances do we have both a red card and a 2 occurring at the same time? 2, right? The 2 of hearts and the 2 of diamonds. So I've counted those 2 cards twice, so I have to subtract those away. And this will give me 30 minus 2, which is 28 out of 52 cards. 4 goes into both of those. What, 7 13ths? Okay. That's how we do the addition rules. All right. Now, what I want to do next is I want to show you what happens if it's A or B or C. What if we go to 3 events, okay? And instead of just putting up the formula, it's kind of a ridiculous formula, I want to show you how we can get that formula using what we call a Venn diagram, okay? So, let's erase this real fast. Let's take a look at these addition rules using Venn diagrams. Does anybody know what a Venn diagram is?
That thing with the circles?
Yeah, the thing with circles, exactly. Okay, so let's look at what we just did. If we had A and B mutually exclusive, this is what our Venn diagram looks like. Here's A, here's B, and the probability of A or B is simply this guy plus this guy. So in Venn diagrams, you kind of want to look at it as an area, okay? So the probability of A is the area of this circle, plus the probability of B, the area of this circle, and you just take them together. And that's the probability of A or B happening, okay?
It's called a what?
A Venn diagram, V-E-N-N.
V-E-N-N.
Okay? Now, when A and B were not mutually exclusive, that meant that there was some overlap. Okay, so now watch this picture. So here we have A and here we have B. And your goal, everybody, is to get everything shaded just one time. Okay? So watch what happens here. If I want the probability of A or B, I want everything just shaded one time. Okay, so when I take the probability of A, I'm shading all of the circle A. When I add in the probability of B, I'm adding in all the shading of B. And what has happened? This little part here has now been counted twice. Does everybody see that? So I have to subtract off that little section in there. And what is that section? That's A and B together. Okay, does that kind of make sense? So I'm trying to get it so that everything is just shaded one time. That's my goal. Okay, let's move to 3. So if they're ME, if they're all mutually exclusive, then it's pretty easy, right? If we have 3 mutually exclusive things, can you guys tell me what the probability of A or B or C is going to be if they're all mutually exclusive? What's the answer here?
P probability of A plus probability of B plus probability of C.
Right. Perfect. Right, we're just going to add up each one, and you get each area one time, and you're good. Okay? So if the events are mutually exclusive, you're just going to do probability of A plus the probability of B plus the probability of C. All right. To do the next picture, I'm going to actually erase the whole board and kind of magnify it so we can see what happens. Okay? So now I want to draw 3 circles overlapping to get the last picture that I want to do today. So I can show you kind of where the formula comes from instead of just writing down the formula. Okay, so let's do the Venn diagram with 3 circles, not mutually exclusive. So here's A, here's B, and here's C. Okay? Your job is to get all of these areas one time. Okay? That's what we're trying to do. If you can give me a formula that just covers all of these little sections one time, that is the formula we want. Okay? So I'm trying to develop a formula for the probability of A or B or C. Okay? You don't necessarily have to draw it out, but if you just kind of follow along with what I'm doing, we should be able to get it together. Okay, the first thing that I'm going to do is I'm going to just take A, B, and C. Okay, so let's do that. So let's do the probability of A plus the probability of B plus the probability of C. Okay, so let's pay attention here with what happens. If I do all of the circle A, okay, that would shade in everything inside of A. Okay, so I'm just going to mark it. That's been shaded once, once, and once. Does everybody see that? When I add in all of the area of B, this has now been marked once and once, but these guys have been overlapped, right? So they've actually been shaded how many times now? Twice. Okay? Then if I add in the area of C, this whole circle, this guy's now been shaded once. These two have now been shaded twice. And this little guy in the middle has now been shaded 3 times. Okay? Now, if everybody's okay with that, I need to start subtracting some stuff because I want a 1 in every spot. I just want everything shaded 1 time. Okay? So let's start subtracting. I'm going to subtract the A and B area. So let's subtract the probability of A and B. Great. So now this 2 becomes a 1, which is perfect because that's what I want. And this 3 becomes a 2. So I'm subtracting off that one little area there. Okay? Now let's subtract off the probability of B and C. So B and C only overlap right here. So this 2 becomes a 1 and that 2 becomes a 1. Great. We're so close to getting a 1 in every spot, which is my goal. Okay? Now let's subtract the probability of A and C. If I do that, what happens? This 2 here, so this is the overlap between A and C. This 2 becomes a 1, which is great, but unfortunately, what happens with this 1 here? It becomes a 0. Okay, but I'm so close. Is there any way I could get that 0 to turn back into a 1? What is that 0? What does that represent? Where A, B, and C all intersect, okay? So I need to add on plus the probability of A and B and C. And that will bring that little section here, 0, back to a 1. Now everything has been shaded and counted just once. And there you have it. This is our formula for 3 events. Okay? So if on the test I say, you select a single card from a deck of cards, what's the probability it's a king or a diamond or a red card? This is the formula that you utilize. Okay? Or you just write out the sample space and say, here's how many kings there are, diamonds, and what did I say, red cards, and just make sure you don't count twice. Okay? But this is the formula. All right, so do that question I just asked you. What's the probability of getting a king? Or, what did I say, red? Or a diamond? There's 2 ways to do it. One way, use this formula. The other way, look at your sample space. There's 52 things. Count how many kings, reds, and diamonds without counting them twice. Okay. Go ahead, try that out and see what you get. Okay, so I want us to do this both ways. So open your book to the whole sample space for drawing cards. What page is that again? Oh, here we go, page 184. So let's do this using sample space first, okay? So we're going to select a single card, and we're looking at kings, reds, and diamonds, right? There's 52 total cards. How many of them are red? 26. If I count all the red cards, have I counted all the diamonds? Yes. Have I counted all the kings?
No.
No, I've counted almost all the kings. How many kings are missing? Just 2, right? So when I do the 26 red cards, that's already counted all the diamonds, and it's counted 2 of the kings. So I'm only missing the other 2 kings. So does everybody see that all we're missing? So the answer to this should be 28 out of 52. Okay? Counting all of these just one time. We've counted all the red cards, we've counted all the kings, we've counted all the diamonds just one time. Okay? Let's see if we can get 28 out of 52 doing it the long method, using this formula we just came up with. All right? So here we go. How many kings are there? 4 out of 52. How many red cards are there? 26 out of 52. How many diamonds are there? 13 out of 52. Subtract. How many red kings are there? 2 out of 52. Subtract. How many red diamonds are there? 13 out of 52. Subtract. How many king diamonds are there?
1.
How many red king diamonds are there? 1. Okay, did everybody see that? So I just went through each one and add this up for me and tell me what you get.
Why do you add that last one?
The the plus, remember from the Venn diagram, plus, and with
Oh.
all three have in common, yeah. So what do we get here? 20 out of 52. And it better be the same as just looking at your sample space, okay? Do whatever's easier for you, all right? So if you have the sample space in front of you, it's much easier just to use the sample space, okay? If not, here's the formula that will find it for you, okay? Any questions on the addition rules for probability? Okay, good.